Today we are going to move to a sequence of lectures on large language models. Not many, like probably 3, 4. And in between, we also have to talk about reinforcement learning a little bit, because otherwise we cannot talk about some of the modern reasoning models without understanding a little bit about reinforcement learning. So that's pretty much the rest of the lecture, except 2 guest lectures. I think the upcoming Monday we'll have Simran to give us a lecture on system ML, which is also quite about transformers, like how do you optimize the efficiency of transformers on a GPU, so on and so forth. Okay, sounds good. So large language models, I guess you always, probably all of you have heard of this word, large language models. This is precisely, I think in some sense, this is all starting from GPT-3. When OpenAI released GPT-3, it used this new paradigm which use autoregressive large language models. So basically we're going to focus on that, autoregressive large language models. We're going to skip some of the earlier versions of transformer which are not autoregressive. And autoregressive basically means that you generate tokens one by one, and each of the new tokens depends on the previous tokens, and you do this, and you model the probability in this kind of like autoregressive way. I'm going to talk more about details. In some sense, you model your language distribution by using a sequential model one by one in some sense. Anyway, so let's. I think the point, our goal is to talk about some details. So I'll fill in more high-level stuff as we talk about the details. So the first thing we're going to talk about is tokenization. This is, just to prepare us to talk about the real meat in some sense. So what does tokenization mean? It means that you need to, these transformers, they are numerical, architecture models, right? So they take in some sense, numerical numbers, right? So, but you have text, and how do you turn text into some kind of things that the models can understand? So, the first step is to tokenize. Tokenize means that you need to decide, what is the smallest unit of the input you give to the large language model. And often it's not a word, right? The most natural thing you can think of is maybe the smallest unit is a character or a word. If you use character level tokenization, then the issue is that often you have so many characters, right? You need so many tokens, so many steps. If you use word level tokenization, then often the issue is that how do you deal with this long word, which are very rare? For example, you have a word called, say, internationalization, right? So if you treat this word as a single word, then maybe it's too rare, and you don't leverage your understanding about other words, right? So if you treat internationalization as one word, then it is different from internationalized. It's different from like a nation, right? And they are all completely different kind of things. And you cannot leverage that. For example, if you understand internationalized, then you should probably understand internationalization to some degree without even seeing more data. And so that's why people don't always use subword tokenization, or don't use word tokenization. Maybe let me give you another example, right? So for example, if you use this, I guess in my notes, there is this word LM, modification. Actually, I don't know whether this is a real word. I think it's a new word that is completely new word. Nobody have used it before 2020, I guess, right? So even right now, it's not that kind of like common. And if you have to treat this word as a unit, then you have to see this word enough times to understand what it means. Right. However, if you treat it as subwords, then maybe you have a token called LM. You have a token which is, you have a 2 unit. This is a token. This is a token. So LM is a token. Implication is a token. Then, in some sense, you have seen LMs many, many times. You already understand it. And then, ification has a special meaning in English. And then you combine these two understanding, you understand the word. So that's much more efficient understanding of the word than just treating this whole thing as a single unit. So, and this happens more often in, for example, biology, when you have this very long word, or maybe in German you have very long word, but actually there are fundamentally many combinations of many subwords. And using subword tokenization allows you to understand each of the subwords, and then you can understand the combination of those subwords as a whole very efficiently. So yeah, so basically tokenization, just means that you have a predefined vocabulary, And this vocabulary is a list of like subwords, right? So for example, you can have, many of this, like maybe A is a subword, is a one of the token, I think maybe like a dog is a token. Pretty much all common words these days is a token. And actually, if you look at actually you can play with the tokenization online. If you search OpenAI tokenizer, OpenAI give you a playground where you can see how the tags are tokenized. And you'll find that actually blank dog is also a token. So, so the blank is actually merged with dog as a token, and and you have so many of this. Typically, this kind of like a tokenization right now, I think for the open source models, we know the number of tokens they have. I think it's often on the order of like 10 to the 5, like 100K at least. I think Qwen 3.5, this is the newest version of the open source models, which are pretty good. I think they have like 250 tokens. I think 250 probably is mostly because, I think 250 is somehow you can represent this token with like maybe 8 bytes in some sense. It also depends on how many bits you can present the tokens. Anyway, so you have this vocabulary, and then you just, giving a long string of text, you just take all the subwords that are tokens and you turn it into a sequence of like segments, right? For example, if you have a dog runs, suppose this is the text you see, and then you'll say this is a token, so this is one part, and then I think blank dog is a token, and blank runs is also a token, and comma I think is a token by itself. So, and every token has an ID, right? So let's say A is probably the ID number 1, dog is maybe the ID number like 356, whatever, and run is some ID, maybe, I don't know, maybe 250. I'm just writing some random number. So everything has an ID. So basically you turn every text into a sequence of IDs. Each ID corresponds to one token. And I think, so in this case, most of these words are actually one token. I think I just checked recently, if you have the word happiness, I think the tokenization will be unhappiness, let's say. I think this part is a token, H is a token, and APINESS is a token for some reason. And maybe another example is this. I already erased it, the ILM imification. And this is another example that we come up with, I don't know actually what this word means. If you have a blast OMA, I think this part is a token, this part is a token, and this part is token. I think this is just because for these biology words, biomedical words, actually every part of the word has some special meaning, and so you tokenize them into tokens. And what is the exact vocabulary? It depends on the model. So basically the algorithm that turns the text into these tokens is called a tokenizer. And every model has a different tokenizer. Not everyone has a different one. Some of them shared the same tokenizers, but generally it's specific to the tokenizer, to the model. And different companies have different proprietary tokenization approach. You probably heard of that recently. I think Cloud, they update their tokenizers so that I think they make the tokenizers more granular to some degree, so that the same amount of text will be tokenized into more tokens. So before it's like 1,000 tokens, now it's 1,500 tokens. I didn't verify myself, but I read some news about this. Assuming they are true, that means that you spend more tokens. You pay more to Cloud Code with the same amount of text. Anyway, so cool. And there are some details about how to come up with the vocabulary and how to kind of like run this algorithm to tokenize. The keyword is called BPE tokenizer, byte paired encoding. So I'm not going to the details because this is just a very small, quick setup. It's not that important. But roughly speaking, the BPE tokenization idea is that you try to, in some sense, you just try to find frequent subwords that are most frequent, right? And you use them in a vocabulary. But how do you decide which one is more frequent and not? I think there's a sequential algorithm. You first go through maybe like the smallest kind of like combinations of like you go through all the characters, and you try to find, I think it's a greedy algorithm. First, you try to find the most frequent, one character thing, and you find the most frequent combination of two characters, and you remove It's a little bit complicated, which let me not try to give you a precise version, but it's kind of like a greedy algorithm that decides which one is more frequent, so on and so forth. And if you are interested, you can look up the exact algorithm. Okay, so that's the tokenization. So that means that from now on, we just assume we have a tokenizer. So every piece of text will be turned into a sequence of tokens. So from now on, like a text, it just means a sequence of tokens, and each of this xi is in a vocabulary. Let's call the vocabulary V. And the size of the vocabulary could be like 250 thousands. Each of this is kind of like an index in the vocabulary. Like, this is the 5th token, this is the 105th token, so on and so forth. Okay, so now the question is, now we go into the next question, which is how do we model this distribution of sequence of tokens? How do we create a probabilistic model to model it? If you think about the support of this distribution, like how many possible combinations that there are possible here. So the number of possible combinations is you have V choice. This is the cardinality of V. You have cardinality of V choice for each of the tokens, and you have a sequence of length t. So you take the power to the t, right? So everyone has V choice, and the V to the power t is the total number of choices. So you cannot assign one probability for each of this sequence, like a discrete categorical tokens, right? Like categorical distributions, right? If you treat this as a categorical distributions, then every choice here will have one probability, and that's just way too many parameters to describe it. So that's why what people do is that people decompose this distribution using the chain rule to write it this way. So you say, suppose I have a probability distribution over the joint of the sequence, then I can write it as the following. So I can say it's equals to P of x1 times P of x2 given x1, P of x3 given x2 and x1, so on and so forth, and P of xt given x1 up to xt minus 1. And this is the so-called conditional probability decomposition. You decompose the joint distribution into a product of conditional probabilities. And you model each of these conditional probabilities. The benefit here is that each of these conditional probabilities is a conditional distribution, but the choice of x2, for example, here is only V. You don't have V choices here. You only have to have a kind of like a softmax or logis over V choices for each of this. Right, so each of this will be, eventually you'll see, is some kind of like you have some logis and you apply some softmax, you get a probability distribution over V choice. So that's what we're going to do. So basically, each of this will be parametrized by a neural network. The input will be what's after the conditioning, right? So the input here is the x1 and x2, and output is the distribution of x3. And this input-output relationship is modeled by a neural network, which is a transformer. Okay, so that's what we are going towards. How do we model each of these conditional distribution? So basically, we're going to describe a conditional distribution P of P sub theta xt given x1 up to xt minus 1. So before going to details, let's treat this as a kind of like a black box first. And let's first kind of like discuss a little bit about the boundary, right, in some sense, right? So it's kind of like there are multiple layers here. So the typical way to parameterize this is the following. So you use a transformer. So basically what happens is that you have a sequence x1 up to xt. And so first of all, these are discrete IDs, right? So each of these means a ID for the token. You first have to turn them into some numerical numbers. So the first step is that you say, I'm going to turn this into an embedding E of x1. And so basically I turn each of the token x into xt into embedding of xt. And what is the embedding? Embedding is let's say d-dimensional vector in the Euclidean space. And this embedding is trained. So basically you don't know what the parameters are. You will just parameterize it as unknown numbers, and you train the model to find the right numbers for these embeddings. So every token in the vocabulary will have a corresponding embeddings. So basically, you're gonna have a sequence of embeddings E1, E2. This is the embedding for the first token, embedding for the second token, up to the embedding for the last token. And in this lecture, I think we're going to use row vectors because I think when you get into the implementations, every vector is actually row vectors in the Python code, even though in mathematics, people often use column vectors. So I thought about this, and I thought just for this, for large language model sections, we'll just always use row vectors, which is more consistent with the practice. It looks a bit weird to me, actually, from a mathematical perspective. And if you read the papers, many of the papers do use column vectors, but I think we'll just use row vectors to be consistent with the code. So basically, every embedding is a row vector. And then you have this embedding matrix. So this is, you have V of them, and each of them is of dimension D. So you have this matrix. And to read off which row you are, you just have to multiply. Either you just read off the ID, right? So if you have the fifth token, you just read the fifth row, or you can multiply this matrix with an indicator vector to get that row, which is the same thing. Anyway, so we'll just read off from this embedding matrix the corresponding embeddings for each of the token. So you get E of x2 up to E of xt. And I think in many cases, often people append, prepend a beginning of sentence token, which is just a fixed token in the very beginning. This is kind of like not always necessary. In some cases, you just don't do it. In some cases, you do it. But let's probably just introduce that. You have a beginning of sentence token, which is one of the special token in this vocabulary. You probably often actually what happens is that your vocabulary is bigger than what is needed. You always reserve a few tokens, actually maybe 1,000, a few thousand tokens for special tokens that you can introduce for special purposes. And you can introduce this beginning of sentence token as x0, so which is always the same. And then you turn them into embeddings. And then what you do is that you go through this transformer, which I will discuss in the later half of the lecture. So this is a transformer. For now, you just think of this as a neural network, which does a lot of computation, machine application, attentions, which I'm going to discuss, a lot of operations, and then you output some logics of, you output some kind of logics at each of the locations. So each of these logics is supposed to describe the conditional distribution before the softmax. So basically, what you do is you say the probability of, so let's just, you say each of these U1 is, let's call this U1 U theta x0, and then P of x1 is modeled as, just the softmax. This distribution P of xi is the, x1 is modeled as the softmax of f theta x0. So the first distribution, which is not conditional, you just get the output from the x0, you get some logic. So this ui is in dimension v, and you take a softmax, you get a probability vector. So this is a probability vector, right, in this simplex of dimension v, right? So the sum, this after taking a softmax, the sum of the entries is 1, and all of the entries are non-negative. So then this is your probability for x1. This is the distribution. Technically, I think the distribution of this is equal to softmax. Okay? And then the same thing, when you have x2 given x1, you say this is equals to softmax of u2, where u2 is the output at the second position. And u2, we'll just call u2 the same as, so you call u2 the output, of this model given x 0 and x1. So each of these UIs, is basically the output for the sequence before it, right? So ut plus 1 is f theta x0 up to xt. So, so basically, generically, p of xt given x1 up xt minus 1 is the softmax of ut. Is it ut or ut plus 1? Ut plus ut, yes, ut, which is the softmax of f theta x0 up to x t minus 1. Okay. Any questions so far?
Is your indexing for u sort of 0 or?
So I particularly chose it to index at 1, yes.
Okay, and so that's this on the right.
Yes. U is just the vector. I think I can just call U. I think it's kind of like I can just call U f theta x0. It's the same thing. I'm not. Did I answer the question?
Yeah, but like 2x, like so. Because after a complement of the next token that is like yeah, what ends up being head out like what like the output in this case what is that?
So I think maybe that's the so I'm just using f theta x0 x1 as a more explicit way to represent UI because I'm trying to express the dependency. So basically I'm saying like I think they are the same thing. Like it's just there are no difference at all in some sense. It's just how you view it, right? Like in one way you just say, I need a notation for the vector, and the other way is I need to interpret this vector as a function of the inputs.
Right. Yeah, I mean that part is clear.
Oh, okay. So maybe I didn't get a question.
Just a probability of like seeing that token as the output is like the probability of that token being present. I guess. So I'm just trying to understand like this probability modeling here. The output is the token that they. We're just trying to like predict the probability of seeing the token.
Yes. So I think maybe. I'm trying to figure out what's the question here. So I think maybe what they're asking is the following. So maybe let's take this one, right? So this is a vector. This is a vector in dimension v. So in a vocabulary size. And after you take a softmax, it's a sequence of numbers which are all non-negative and they sum to 1. So, and what this really means is that p theta of xt is equals to 1 given x1 up to xt minus 1. The chance to see the first token under this probabilistic model, parametric by theta, is equals to, this is a vector, the first entry of this vector, right? Is equals to softmax f theta x0 up to xt minus 1, indexed by 1. This is the first entry of this vector. And you have many other entries, right? Each entry is like, you have another entry, softmax f theta, 2, and that is equals to p theta of xt is equal to 2, the chance of seeing the second token given x1 up to xt minus 1. And you have so on and so forth. Does that answer the question? V is this V absolute value is the size of the vocabulary.
So is this like a mass attention because the modules are conditional on like the previous one? It's not like ones after it, right?
Yep. So this is a causal model so far, but I haven't defined the transformer yet. But I'm insisting that this is only. So guys, this is one of the reasons I'm using this notation. So I'm insisting that ut is only a function of x0 and xt minus 1, but not a function of the later inputs. So, but that will be guaranteed when we introduce the exact inner working of this transformer.
Where do we write this function as a function of x, as none of the embeddings that we defined before, and also like doesn't this do not these embeddings also depend on the following x's?
Okay, good question. So the second question is easier to answer. So the embeddings is only a property of this x, right? You don't have to see any other things, right? It's just actually, it's literally, if this is the first token, then you just read the first row of this matrix. If this is the 10th token, you read the 10th row, and that's your embedding. No any other dependencies. And why we are writing this as functions of the x, but not the embeddings, that's just sometimes the embeddings is the inner working to some degree. I'm just trying to give you more. I'm trying to unpack it a little bit, right? So if you don't have to unpack it, you can work with the text. Yeah, that's just the representation. Yeah, and it's one-to-one, so in some sense there's no difference. Okay, so this is a full description of the probabilistic model. Once you have this probabilistic model, you can compute the maximum likelihood given any data. We can say, I have a data distribution, I have a data point, a sequence of data. I can see under this probabilistic model, p theta, what is the chance of seeing this data. So that's what you need for computing do the training, right? You need to compute the likelihood, and then you maximize the likelihood as a function of theta, right? So let's briefly discuss, for generation, right? So suppose you already have the generation or decoding. Suppose you already have the model, then a model theta, then what do you do? So as you can see, the most natural thing is you just keep generating x1, x2, x3, so on and so forth, right? You just say, I'm going to generate x1 first from this, p, say, softmax, f theta, x1 up to x0 up to xt, I guess I just write generically. So you generate xt minus 1 from f theta x0 up to xt minus 1, right? You do this sequentially. Sometimes people draw this in this way. So you say, oh, you have x0, you first go through the transformer, and you get x1, and you feed x1 back to this transformer, right? So, and then you generate x2 by sampling from the softmax, and then you feed back. So that's kind of why it's called autoregressive, because you have to, like when you are generating, you don't have the sequence, right? When you are computing log likelihood, you already see the whole sequence. You are just trying to figure out what's the chance of seeing this sequence. But when you are generating, you start with nothing. And then you have to generate your sequence yourself. And that's why you start with the beginning of sentence sequence token, and then you generate first token, and then you give the first token back to the transformer and compute this softmax. And then you generate a second token, you do a sampling to generate a second token, and you give it back, and you keep doing this. So that's the autoregressive generation. And sometimes, this generation can only start from certain parts, because in many cases, you are not generating from nothing. So you are given maybe a few tokens, maybe you are given, sometimes it's called prompt. So prompt is like something the models are given. It's maybe like a question, an instruction, so on and so forth. You say you are given x1 up to xk. And then the model is supposed to complete the generation. So it starts with xt plus 1. So xt plus 1, so this is given. And then you start with xt plus 1. You first generate xt plus 1 from this softmax of the f theta x1 up to xk. And then you generate xk plus 2. And then you do the same thing. So it doesn't have to be always from the beginning. And then there's another small thing, which is that when you generate, you don't necessarily have to always follow the same model. And there's one thing that you can deviate from it, which is that you can add additional temperature where you say, as opposed to generating from the original probabilistic model, I'm going to divide this by a temperature tau, or t sometimes. What does this mean is that you don't change the orders between these choices, right? So this is this f theta is a vector, right? It's a v-dimensional vector that describes the logits for each of the tokens in the vocabulary. And when you divide by tau, you don't change their relative orders. The bigger ones are still bigger, the smaller ones are still smaller, but you change the the scale. So, so for example, before you could have like a, so suppose, f theta x0 up to xk is equals to, let's say, maybe like a 2, 1, minus 1, something like this. And if you divide by tau, let's say suppose you divide by tau, which is very, very small. Suppose tau is almost 0. Then after dividing by tau, like if you divide by tau, then what happens is that maybe this becomes 200. This becomes 100. I'm giving a concrete example, which is a little bit unrealistic, but to demonstrate the point. And what's the difference between the softmax of this vector versus the softmax of the readjusted vector? The difference is that the softmax of this is much sharper. So maybe let me just give you an example here. So if you just have, let's say, maybe let's just have 3 dimensions so that it's easier to demonstrate the point. So if you do softmax of this vector of 2, 1, minus 1, what happens is that you get, in some sense, you get exponential 2 over exponential 2 plus exponential 1 plus exponential minus 1. That's the, after softmax, what's the probability of the first token, right? And the second token will be exponential 1, exponential 2 plus exponential 1 plus exponential minus 1. Right, and the third one will be the same denominator, the different numerator, right? So that's the softmax of this. But if you take the softmax of the 200, 100 minus 100, suppose you do that, then this will give you exponential 200 versus exponential 200 plus exponential 100 plus exponential minus 100, blah, blah, blah. So what's the difference here? The difference is that in terms of the 3 numbers, in terms of the order, it's always like this is bigger than this is bigger than this, right? Because 200 is big, 2 is bigger than 1, 1 is bigger than minus 1. The order is always maintained. But the relatively scale is different, because here you can see exponential 200 is way, way bigger than exponential 100. The difference is like so astronomical. Like it's the difference is too big, so that these 2 numbers are just so small compared to exponential 200. So they are even negligible. So basically, in this calculation, these 2 numbers don't even have to show up here. Like they don't even matter. So you just get 1. So basically, the first token will just have probability almost exactly 1, maybe 0.9999 something. And then if you look at the second entry, which is exponential 100 divided by exponential 200 plus exponential 100 plus exponential minus 100. Again, everything is negligible compared to exponential 200. So this is not very useful. This is not very useful. This is kind of like close to 0. So basically, this entry will be 0. So that's why after you divide by tau to make this bigger, then this is just approximately 1, 0, and 0. So that's what I mean by it's much sharper. So you sharpen the distribution to make it most of the distribution to be the probability mass to be on the most likely token. And however, here exponential 2 and exponential 1 are not that different. If you compute this, you'll get something like maybe the first one will be like maybe 0.7, the second one will be 0.3. I don't know. Like we can use a calculator to see, but it will still be like this one is bigger than this, and the second one is bigger than the third one. But it won't be like all the mass is on the first token. So basically, what I'm trying to say is that if tau is a small number, so that you amplify the logits, then you are sharpening the resulting distribution to make it more like a deterministic distribution. And then as a result, you are just generating, you are just sampling from the most likely token. You are taking the max as opposed to sampling from it. So, and that's actually what people actually do. Like they say, basically, like I think actually in API call, you have the choice to choose the temperature. And if you choose a small temperature, it means that you want more deterministic generation. If you choose the temperature to be 0, it means that your generation will just be always deterministic. Every time you take the largest most likely token, and then keep going on, right? And of course, you can also change the temperature to be smaller than, bigger than 1, which makes the distribution more softer, so that there's you focus on more the long tail, like you can generate more tokens from the tail, so you have more stochasticity and uncertainty in your generation. Sometimes that's useful because you want to encourage some diversity in your generation, and you do that. Especially in the RL, sometimes you have to do that. Cool. Okay, sounds good. And sometimes there are also other ways of sampling, which is probably I shouldn't go into details. There are some notes in the lecture notes. So another way to do it is that you this vector right now I have 3 dimensions, but actually it's like the dimensionality is v, right? Like which is like 250 or something. You can take top k and then drop all of the other dimensions. So you only sample from the most likely k tokens, and you renormalize the distribution. So basically the first k tokens may not cover all the probability mass. So but still that's probably easier to generate because you don't want to generate too rare tokens, so you just drop everything below top k and then generate. Okay, sounds good. So I think I'm probably and then okay. So once you have all, so this is the generation, and then for the training, I think I already kind of like describe it a little bit. So when you do the training, you just compute the log likelihood, the negative log likelihood. The negative log likelihood. And you say this is a log. So if you have example x1 up to xt, so the minus log p theta x1 up to xt, capital T, is just minus log the product of all of this, right? P theta x1, P theta x2 given x1, so on and so forth. And this is the minus the sum of the log of the P of xt given x1 up to xt minus 1. And then you change this to log of the softmax of P1 of this f theta. And here, this xt is a particular choice of xt, right, which is seen in the data. So that means you are looking at the xt's entry of this softmax. This softmax will give you the probability for every possible tokens. And then you are only interested in the probability to see that particular token xt. So that's why you're looking at the xt index of that vector. And that's a single scalar. You take the log and you take the sum over t, and that's your loss function. And then you can optimize this loss function by, for example, some optimizers like SGD or IDEM. We didn't discuss IDEM in this lecture, which is an extension of the SGD optimizer, but mostly you can just call the optimizer as a black box to optimize the loss function.
In this case, like we are basically just optimizing for the property of the last vector, last entry in that vector. So the way that we have, it should ideally be
it's not actually not the last one, right? Because this is sum from t to 1 to capital T. The little t and larger t. Okay, sounds good. Okay, so then in the next 30 minutes, I'm going to tell you what this function f is, right? Or maybe what's hidden in this transformer. What's the operation we have to do to compute the logs here? And it's pretty complicated, so it probably takes more than 30 minutes, but I'll see how much I can do. So any questions before that? Okay. So at a high level, this transformer has multiple layers. And so you start with like EX1 up to EXT. And you first apply a so-called attention layer, which I'll define. And then you apply the so-called MLP. So first of all, the attention layer, the attention always takes in a sequence of vectors and output a sequence of vectors. So you output a bunch of vectors. At each position, you output one vector. And then each of these vectors will go through a MLP. MLP means like a multi-layer perception, which is just a two or three layer network. And each of these vectors will go through this MLP. And then you apply another attention. This attention will take in many vectors, and then output a sequence of vectors. And then you do the MLP. So that's the high-level structure of this attention. And eventually, you have to output. Remember, eventually you have to output a sequence of vectors. So basically, you do enough of these alternations between these two, and eventually you have this MLP, and you output some vectors U1 up to UT. Right? And you alternate between attention and MLP. That's the high-level idea. And I think we'll focus most of our energy on defining attention, which is kind of like the most new thing, right? Because MLP is just a two-layer network with some special kind of gating or kind of like some kind of like a special activation functions. And another small thing is that the MLP are sharing the parameters and they are applying independently. So each of these vectors is processed by the MLP in an independent fashion. There's no kind of dependencies between positions when you apply the MLP. They are just very separate operations. So the only way that you are using, you are kind of like you fuse the input from different positions or different time steps is the attention. So the attention will look at all those vectors and process a little bit and then output a sequence of vectors. And the MLP is very parallelized and parallelizable and independent. Okay, so now let's define attention. This entire thing will be treated as a single system. So basically, once you define the architecture, you apply the auto differentiation. You train this whole thing as a gigantic network, yeah, end to end.
But it's like a little bit different than the neural network that we've been seeing so far, which is like one, like integrated neural network. I guess the gradients and stuff are going to work a little bit different.
Yeah, but the auto differentiation still works. So the auto differentiation, I think, as we discussed, if you remember, like it's kind of like fundamentally it's claiming that if you have a way to compute your forward path, as long as there are compositions of many different components, like a basic components, you can compute the backward path the same way. So here is indeed a composition of many small arithmetic operations because, as you see, the attention layer has many small matrix multiplications, and the MLP has many matrix multiplications, and you can automatically differentiate. Okay, so now let's talk about attention. So for attention, one thing to remember first is that the type signature is that you input a sequence of vectors to the attention, and then you output a sequence of vectors. And we're going to start with the so-called single head attention. So the single head attention is like this. So you first have a input as a sequence of vectors. Let's say H1, say in up to HT in, and you want to output H. I'm trying to define the type signature. So you output H1 out up to HT out. And what you do is the following. So the first thing is that you turn this input vectors into a set of query, key, and value vectors. So you define. So basically, you say H1 in. You multiply it by a matrix WQ. This is a weight matrix. This is a parameter. And by the way, let's treat all of this as row vectors, and then all the multiplication is on the right-hand side as opposed to on the left-hand side. So every vector is a row vector, and you multiply on the right-hand side, you get another row vector. So this H in, let's say this is like a dimension D, RD. Let's say R1 by D, and this WQ is in dimension. So this is in R1 by D, and this WQ is in RD by DH. DH is a parameter, it's a dimension you choose. And then the resulting thing is called Q1, which is in dimension DH, maybe 1 by DH, depending on how you think about it. And you can do this for every index, every time step. Here I'm only doing it for time step 1. You can do it for time step t, so you have Qt. So basically this gives you a sequence of vectors Q1 up to Q capital T. Each of them is in dimension 1 by DH. And these are called queries. And you do the same thing for keys and values. So keys, let me define them first. So it's the same thing. You say the HT in multiplied by a so-called key projection matrix, WK, and that's your KT. And the dimensionality, I think, is the same. So this is also in the same dimension, and the KT is in the same dimension. And it's the same thing for value vectors, not value functions. HT in times W V. So in some sense, maybe this is the right time to talk about some of the intuitions, for the attentions, which is not that obvious because eventually it just works, like nobody really knows exactly how it works. But the rough intuition is that you have to have some interactions between these inputs to make it meaningful, right? Because if everything is independent, then you're just dealing with all the time steps independently. So that's why you have to have some interactions. And the interactions sometimes is about how do you kind of like retrieve or kind of pay attention to each other. So that's actually how the word attention comes from. So basically, when you are processing maybe this vector, you probably should attend to or pay attention to some other vectors which have relevant information. And which one you pay attention to is what we're going to decide here with this query and key and vectors. So in some sense, intuitively, what attention will do, which I didn't show you yet, is that you try to, for processing each of the vectors, you try to figure out which are the relevant vectors that has relevant information, and then you pay actual attention to those vectors. And then you compute the output depending on those special vectors to some degree. So that's what we are trying to do. And to kind of like decide which one you pay attention to, you have to prepare these queries and key and value vectors. And how to use them? So use the query and keys as a way to decide which one you pay attention to. So basically, let's say, suppose you have the t position, right? I want to decide what the t position should pay attention to. And the way to do it is you say you compute the query Qt. This is the query at t position. And you multiply the query with the keys at all the other positions. So maybe I will just draw it. So you have queries Q1 up to Qt, and one of them is Q little t, and you have K1 up to KT. And you multiply Q's with all the K's. So you have Q1 times, K1 transpose, Qt times K2 transpose, and Qt times K capital T transpose. And there is sometimes there's a scaling factor here to kind of like normalize this in a way that makes it a little bit more kind of like well behaved. But I think for the moment you probably don't have to pay too much attention to the scaling factor. So the important thing is that you are taking the inner product between Q's and each of the other K's. And this Qt transpose K transpose is actually the inner product because Q is a row vector and K transpose is a column vector. And you are taking the inner product between these row vectors and the column vectors, and you get one scalar out of it. So this is all of these numbers are real numbers, right? So this is in RT. So you have T real numbers, and then you take a softmax over these T real numbers to turn it into a probability vector. So then you say, I'm going to do a softmax. say softmax of this whole thing. And now you get what? You get this is a vector. The dimensionality here is RT, and each of the outcome of the softmax is a sequence of numbers, right? And there are T numbers, and all of these numbers are non-negative, and the sum of them is 1. So it's a probability vector over T positions. And if you see a large number, it means that, let's say, suppose this number is big, it means that this number is somewhat big compared to other ones. It means that the Q's and K's have like more higher inner product, right? And it means that you should pay more attention to K1, right? So basically, if any of these entries is big, it means that intuitively, Qt needs to pay more attention to K1. And that will be reflected by the probability vectors because the corresponding probability will also be high. And so I think let's call this, I guess I have a notation here. So let's call this, let's denote this to be PT1, PT2, up to PT capital T. So each of the PTI is non-negative, and the sum of the PTI over I from 1 to T is equal to 1. So this is a probability vector. And if any of these entries is big, it means that we should pay more attention to that particular position when processing the little t's query. And then how do you turn this? How does this relate to the final outcome? So finally, once you have this, then you say the output at t's position, which is a vector, is using these probability vectors to weight the values. The values is v's, which we are defining here, right? VT. So you say it's PT1 times V1 plus PT2 times V2 plus PTT times VT. So basically, if any of this probability is much higher, then you are multiplying this high probability with the corresponding value at that position. So basically, you are using the V, right? If, for example, if this number is very big, then you are using V2 a lot in the output at time t. So you determine them by multiplying the matrices, and the matrices will be trained. How do you attend to each other is also trained. So you're only giving a template in some sense. It may be that it could be that all of these are 0, then you are not doing anything with it, and then your network, the loss function will be not good, but it's still a valid network. It's just the loss is not good. Yeah. So eventually you are going to train the model to behave well, so basically the training algorithms will choose the right W so that this mechanism is doing the right thing.
This interaction is different from what could be done in by itself.
So let's try to articulate. I think it's a good question, but let's try to articulate so that we can answer it. So what's the
Multiplication of this data.
Yeah.
So why a particular multiplication that the same as here that would be available for the NLP when you train it, and it's not finding it, so we need to push this structure.
So I think you are asking why you need such an architecture, but not just only using MLP, for example, right? That's one way to rephrase the question. I think, so if you are only using MLP in this way, suppose you remove all the tensions, you're only using MLP in this way, then there's no interactions between different positions whatsoever. So there's no chance that it's going to work, right? You are just applying separate networks for each of the tokens. There's no chance you can understand the dependencies, the meanings, right? There's no chance I can just give you individual words and you can understand the sentence. There's no chance, right? So you do have to have a model that can read all the tokens, and use and study their kind of correlations and combinations, so on and so forth, right? But there are other possible ways to deal with that. For example, what if you use a gigantic MLP that takes in all of this? Maybe you concatenate all of them, and you take in one MLP, right? So for example, you just concatenate all of these tokens vectors into one long vector, and you go through a network. So there are several issues with that. One is that you will have way too many parameters, because your sequence length maybe sometimes even millions. Then if you have a million by million matrices in your MLP, it's going to be way too big. Right now, the MLP is actually very small. It only takes in a vector for one position. It doesn't even depend on t. And another thing is that not only the size of the MLP is big, but also the size of the MLP also changes over as you change the sequence length, which is also very undesirable. Because, for example, if you train with sequence length 1,000 and then you test with sequence length 1,001, then you have to change your parameter count, which is not good. And here, if you really look into details, you'll find out that the number of parameters doesn't depend on the sequence length.
You have this gigantic MLP
Yep.
that is too big to compute.
Yep.
But you kind of know that there is some structure, because there are like words that match other words. So this is kind of trying to learn this structure to make it like more efficient to compute.
Exactly, right. So you know that if you have sufficient compute, probably a gigantic MLP will work. If you have sufficient data, so you don't overfit, and you have sufficient compute, then there is some MLP that can actually solve this problem. But that's too expensive. So you need to prescribe some structure so that you can reduce the complexity, right? And this is the prescription we have. But you still have to leave enough flexibilities. You cannot just say, for example, one way to do it is you just say, let's average. Then there's no parameters. You just prescribe too much, right? You dictate too much. Then that's not good. So it's kind of like you need to strike a balance between how much structure you introduce and how much flexibility you give the models to figure out. Yeah. Yeah. Any other questions? By the way, there's actually, in the history, there was actually other ways to deal with this sequence. For example, you can use a convolutional network on this, which is kind of like MLP. So you have use a MLP, but with a specific receptive field, so that each time you only see a kind of like a window. I think there are still papers that says that that's not a terrible idea. Actually, if you use a convolutional network, it actually can work to some degree. It's just not as good as this one, And also you can see like there are also other, probably we'll talk about that later. So there are other variants of tensions that does similar stuff but have better efficiency. Anyway, so let's continue. We are not done yet, actually. This is only a so-called single head attention. Actually, the real thing is a little bit more complicated. But let's see. Before I go into that, let's see. So I think you can see the notation here is very messy. So let's try to simplify it a little bit so that we don't have to always work with this messy notation. So one typical way that people simplify this is that you try to organize all the queries into a matrix. Recall that each of the queries is a row vector, and if you put them all in a matrix, then this is a matrix of dimension t by dh. And you can put all the keys into a matrix, and you can put all the values in a matrix as well. Right, so and then you can write this h out. The output sequence vectors, as a kind of like a also as a matrix is, in some sense, you do a softmax of the row of this QK transpose divided by C matrix times V. So here basically this QK matrix, QK transpose matrix, is the family of QI times KJ transpose divided by C. So every entry is of this form, which is kind of like these guys. And then if you do a row softmax, that corresponds to this softmax. And then if you multiply by v, it means this linear combination. I think we don't have enough time to go into the details, but you can double check. It's just a very basic linear algebra. It's just you are rearranging, it's mostly just notations, right? So this Q case divided by C matrix is the inner product between the queries and keys, and then you take a row-wise softmax to get the probabilities. So after the softmax, this matrix becomes every row is a probability vector, and then you multiply that with the V to take the linear combination of V's. There's one thing that we kind of cheat a little bit here, which is that if you look at this architecture, then it's not true that the teeth output only depends on everything before it. There's no this kind of like a autorecursive kind of like properties yet, right? Because the output at time t depends on everything, right? It depends on capital T, even the last input. V capital T is a function of the last input, and the output at time t depends on the input, depends on Vt and it depends on Ht in. So basically there's no kind of like this dependency. So then what you do is you say you introduce the concept of masking to make sure that there's no this kind of like a wrong dependency you want. So basically what you really want to do is that you just in some sense, for h little t, you want to delete everything after time t. So basically, let's say before you have this, pt v t plus pt t v t, pt capital T v capital T. So basically, you say these dependencies are invalid for me, so I just don't have them. So basically, you just delete all of this. And then you renormalize this piece so that the sum of this piece got normalized to 1. So that it's still a linear combination or convex combination of the V1 up to Vt. So that's pretty much what you do. So you just say if the dependency is not good, you just in some sense mask them out. And mathematically what you do, actually also implementation-wise, what you do is through this masking, which means that you add a masking here. Maybe let's use a different color to show the diff. So you add a masking here. I need a different better color. Okay. So you add a mask here so that you can mask out the, let me see, you can mask out half of this matrix. So you have like a Q1 K1 transpose, Q1 K2 transpose, so on and so forth. And Q1 K2 transpose is not valid in some sense because you are attending to something you shouldn't attend, right? Q1 shouldn't be able to see K2. So basically you add this masking matrix. What you add is that you add minus infinity. You add minus infinity here. And for Q1 K3 transpose, you also add minus infinity, so on and so forth. And then in the next row, you have Q2 K1 transpose, which is good. You have Q2 K2 transpose, which is good. And you have Q2 K3 transpose, which is not good. So you add minus infinity here, so on and so forth. So basically, everything here will be adding additional minus infinity. So basically, this upper triangle part of this matrix will be all minus infinity. And then by adding minus infinity, you just mean like you turn it into minus infinity, right? Any number added by minus infinity is the minus infinity. And then what happens is that, or in other words, it's kind of like you are just trying to add all of minus infinity to all of this part. And then when you turn all of this into minus infinity, when you do the softmax, this part just doesn't help, doesn't change, doesn't by this part I mean like everything after t, right? So everything after little t, you turn them into minus infinity, and after you do the softmax, they become 0. So because exponential to the minus infinity becomes like becomes basically 0. So that's why in this P, so everything after PTT, everything after here will become 0. And the sum of the rest will be 1. So that's exactly how you achieve this, because basically the linear combination of the rest of the terms doesn't matter because their coefficients are 0. Yeah, we are masking this because you shouldn't, in this autoregressive model, you don't allow the output at time t to depend on anything that is after t. So you have to respect this kind of like a sequential dependency. So, in generation, you are not able to see the future tokens to generate a current token. So, so every token can only depend on every things before it. So that's why we have to mask it out. Okay, we are almost done there. Okay, so, okay, so this is the so-called single head attention. And we have to make it a little bit more complicated to even finish the attention part. So then what we do next is that, maybe let's erase here. Let's just say. So in some sense, what we are doing here is like we have H1 in and HT in, and we go through this single head attention. I guess in the note I call it attention 1H, and you get this H out, H1 out, up to HT out. That's what we defined so far. And in practice, you have multiple copies of this single head attention with different weight matrices. So you get another copy of the single head attention. Maybe let's call this single head attention 1. This is called single head attention 2. And they have the same input. And then you get another copy of the output. But here, by copy, I don't really mean literally copy because then it's not useful. So what's the difference between this and this is that the weight matrices are different. So basically, this WQ, WK, WV for these two copies of the tension are different. So that's why they're not really literally copies. They are just like you have another version of it. And yeah, so in some sense you should index this by something else because the output will be different, right? So maybe you should index this by let's say this is, because this is the first attention, you say H11 and HT1, and this is H12, HT2. And you also have another one, and you get H13 up to HT3. So when you have so many copies, you have several sequences of vectors, but eventually you only want one sequence of vectors. So you have to combine them in some way. And the way to combine them is that you concatenate these three things. So you concatenate H11 out, H12 out, I think how many, each of these is called one head. So you have, let's say, NH head. So this is attention N sub H. So you concatenate all of these vectors, and you get, and then you multiply that with another projection matrix, and then this will give you the final the output at 1. So that's the final output at position 1. And you do the same thing for position 2, where you concatenate maybe these guys, and then you do a projection, you get the output at position 2. So in some sense, this is just give you more power to compute different kind of like kind of attention. In some sense, I think actually in practice, I think the intuition is that maybe each of these attention is doing single head attention is trying to pay special type of like is doing some special type of job, right? For example, maybe here it's trying to find out which entity in the past passage matters to me, and here this is trying to find out, which what are kind of like the sentiment of the past passages, and which part of the sentiment matters to me, so on and so forth, right? So each of these attention probably pay attention to different type of information, and then eventually you aggregate the outcome of all of this information into one big vector, and you project it into a single output. Cool.
The second attention is the output of the first one.
No, they are all parallel. Yes.
But
They are parallel, and then you aggregate. So, and all of this is in one of this. And then, so basically in one of this you have multiple parallel heads, and then next round you have another number of parallel heads. I think the number of heads is maybe on the order of like maybe at most 100, I guess. Let me think about this. I think something on that order, I think. Yeah.
One more question.
It also depends on the model size, of course, right? I think the biggest one, I don't know whether 100 is for which model size. I think maybe for like 100 billion parameter models, you have 100 heads. Yeah, something.
Yeah, and you said you have multiple heads because just to have bigger unit.
Yeah.
I'm like thinking like why don't we have just like a bigger weight matrix, and then you can use the same head for that bigger weight matrix. You can have a bigger. I can tell you that the CNN case that you probably want like a big CNN.
Yeah, I think I don't know exactly what's your proposal, but maybe it sounds like a simplified answer, but like many of these proposals has been considered in various ways, and some of them are and most of them are for efficiency perspectives, because eventually you can just have as we discussed, if you really don't care about efficiency, you can just have a generic, very gigantic networks, right? So all of this kind of like special structures to try to use your parameters in the right way so that you can use it more efficiently in some sense. Okay, so and then so I guess let's just give me 2 or 3 minutes to talk about some very quick things. So one thing is that actually when I draw this, it's actually a little bit more complicated than just doing this. So because there's also a residual part in this kind of like how to combine the MLP with attention. So so actually what you really do is that you say you apply so after you do the attention, you do some kind of like normalization here. So there's a normalization layer. Often this is using the RSM norm that we briefly discussed in one of the neural network section. And then you apply MLP, and then you add the residuals back to this. You kind of like in the residual network that we discussed. And then you go to the next layer. And there are different ways to kind of like add the residuals. You can add the residuals after you do the attention or before you do the attention. So there's something called pre-norm and post-norm thing. So I guess the details you can check out the lecture notes. So there's some kind of like orders on how when you apply the normalization, residuals, and attention, so on and so forth. And finally, I think one important thing, especially for the next lecture about the system ML perspective, is that we should try to quickly think about the computational efficiency here and the memory footprint. So how many operations we have to do, especially as a function of t. As a function of other things, it's actually relatively easier because as a function of the number of parameters, like all of those is kind of like it's all multiplicative and linear in some sense. The main important thing is what is the dependency on t. And you can see that for each of the t's position, you have to compute all of these inner products. So for each of the position, you have to compute capital T inner product. So and you have capital T of these positions. So that means that you have to basically do a t-square dependency, right? So or in other words, even this matrix itself is a T by T matrix, capital T by capital T matrix. And each of these entries requires some inner product. So I think the dimension, if you still remember, the QIs or the QTs are in RDH, and you need to compute T square of these inner products. So basically the number of operations is T squared times DH. Dependency on DH is less relevant, less important to some degree. The dependency on T squared is very important because this means that if you have capital T being 1,000,000, it's going to take 1,000,000 times square operations, which is prohibitive. So, and this is one of the issues with the long context issues probably have heard of, like I think when you are using ChatGPT or Cloud Code, you see the context, and then after some point they say, let me compact my context, right? And the reason is that you have to shrink the context, otherwise your computational efficiency is too bad. But of course, in the real production system, it's not like all of this capital T is really, like there are other ways to reduce the dependencies. I think in practice, I don't think necessarily it's T squared. It's probably more closer to linear in T because there are other variants of transformers that can reduce the dependency on T. I think in the next Wednesday, we're going to discuss a few things that can reduce the dependency on T a little bit. Exactly how you do it, we don't really know in some sense because there are a lot of open source papers that propose different approach. At least I don't know exactly which one is used in open and Anthropic. And another thing is that what is the memory usage here? So the memory usage, at the first side you have to spend T squared memory because this matrix itself requires T squared memory. But that actually can be reduced because you don't have to actually compute the whole matrix one by one and then do the multiplication with V. So in some sense, to some degree, you can do some part of this matrix and multiply with part of the V first, and then you don't have to save that part of the matrix. You can compute the second part. So, and the idea is called flash retention, probably you have heard of, which is a way to reduce the memory footprint in these systems. So yeah, I think that's, but like some of these kind of like ideas do have a trade-off because when you reduce the for example, if you change your architecture to make the dependency on T squared better, for example, we'll discuss some of this on Wednesday. So if you change the architecture, the dependency on T is better, but your architecture is less expressive, and then you may lose some performance to some degree. Okay, sounds good.
Thank you.
Yeah, thanks.